Hello, honors topics and physics students. Today we're going to be talking about a particular type of wave, and that wave is sound. Certainly an important part of most of our lives. So what is sound? Sound is a longitudinal wave, also known as a compression wave, which means it consists of compressions and spaces where it's the pressure is lower, which is rarefaction. If you look at this, it actually almost looks kind of 3D, kind of cool thing, but it's not really. Well, I mean, it is 3D, but it's not like these are higher and these are lower. This is just more compressed air, and this is less compressed air. So what is making the sound? It's this vibrating object here. Now this is vibrating very, very slowly, and typically sounds are created by things that are vibrating at much higher frequencies than this, but you can see when it pushes towards the air, it creates that compression, and then when it relaxes back, it creates the rarefaction, and here's it creating the rarefaction right now. So any vibrating object creates sound. How do we hear sound? Well, that vibrating object creates compressions and rarefactions in the longitudinal wave, and then that reaches our eardrum. And when a compression reaches our eardrum, it pushes it back, and then when the rarefaction reaches our eardrum, the eardrum goes the other way, vibrating it essentially. So when the vibrating air meets our eardrum, it vibrates it at the same frequency. So what makes a sound loud? Okay, what makes a sound loud? What is different about this wave as opposed to this wave? It's got the same wavelength, but it has a greater, down here has a greater amplitude. The compressions are more compressed. So that is something I would know, is that it's the amplitude of the sound that creates the loudness of the sound. Okay, what is the difference between a high-pitched and a low-pitched sound? Well, that's the frequency. Okay, and different frequencies create different wavelengths. So this would be a higher-pitched sound over here with the shorter wavelength, and this would be a lower frequency over here with the lower frequency with the longer wavelength. So. And just as there are frequencies of light that we cannot see, for example, we can't see infrared or ultraviolet light, there are frequencies of sound that we can't hear. We can hear typically between the range of 20 hertz to 20,000 hertz. Now, if you listen to loud music or as you age, your hearing decreases, and typically decreases in this high frequency range, and you lose it. I can only, just because of my age, I can only hear to about 16,000 hertz, but many kids can hear 19, 20,000, that sort of thing. Now, if I were to ask you, if a high frequency note and a low frequency note were played at the same time, from the same distance, which would get to you first? High, low, or same time? Alright, trick question almost. Remember, the only thing that affects the speed of the sound, the speed of a wave, such a sound, is the medium. So they would reach you at the same time. So all sounds travel the same speed in air at a given temperature. And at room temperature, the speed of sound in air is about 340 meters per second. Frequency and amplitude do not affect the speed. It's only the medium. Can you hear sound? Normally we hear sound in air. Can you hear sound underwater? Yeah, sound travels underwater. Could you hear sound through a metal? Yeah, if you put up a vibrating metal piece to your ear, you could hear it. So these are the speeds of sound in different mediums. So here we've got air, and here we've got helium. What do you think? Do you think sound's going to travel slower, faster, or the same in helium? Okay. Well, at the same temperature, helium atoms are lighter, so they're actually moving more quickly. So the speed of sound is actually faster in helium. If we look at air at a warmer temperature, air at 0 degrees C is 330. Air at 20 degrees is about 340. So as you heat air, the speed of sound actually increases in it. Okay. Now, compared to the speed of sound in air, let's say 340, do you think sound is going to travel faster or slower in water? Okay. It's actually quite a bit faster. And that's because the water molecules are closer together than air molecules, so they're able to transmit that faster. Okay, what about aluminum? Do you think it's going to be faster or slower in aluminum? Okay, which is obviously a metal, a solid. It's actually, again, quite a bit faster. And in diamond, it's even faster. So, in general, and speaking of which, in a vacuum, and by vacuum I mean there's no air, no nothing, there's no air or anything like that. There's no sound because there's no molecules to transmit that sound to create the compressions and rarefactions. So, all right. So, in general, the speed of sound is the slowest in gases and the fastest in solids. I'd probably make a note of that too. Okay. All right. Okay, so let's say a lightning strikes. How long after the flash will you hear the boom if the lightning was 1 mile or 1,600 kilometers away, assuming that the temperature of the air is 20 degrees and the speed of sound, therefore, is about 340 meters per second? Well, we'll assume that the light travels instantaneously, which is not perfectly true, but it does travel very, very fast, so that we'll get to us really, really quickly. Sound travels at, again, 340 meters per second, so using the equation speed equals distance over time, we get that the time is about 4.7 seconds. So that's why there's that saying you can count the number of Mississippis after the flash until you hear the boom, and then estimate about how far away the lightning strike was. So for about every 5 Mississippis, 1 Mississippi, 2 Mississippis is about a mile. Okay. Let's see. So on to what happens if the source of the sound moves a little bit. If it's not moving and I drop a rock in a pond, the sound waves or the ocean waves, the water waves, radiate out all from the same point. Okay? If that rock is moving as it's bobbing up and down, you see something different. You see that the waves bunch up on the side that it's moving towards, and you see that they're spread out away from the side that it's moving away from. Okay, now note that this does not speed up the wave, okay? It's just being emitted from a different location, okay? The waves aren't traveling any faster because the wave speed only depends on the medium, which in this case is water. Okay, now if we look at the perceived frequency of the wave, if we look at the perceived frequency of B, okay, B is going to perceive a very high boom, 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 boom frequency, whereas A is going to perceive a low frequency, boom, 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 boom. Okay. So there's going to be if this was a sound wave, the observers would hear a different perceived what? Okay, what is the frequency effect? It'd be the pitch. Okay, so you've certainly had this happen before. As a car or something like that was driving by you, you hear the frequency of its engine noise, or in this case, of an ambulance. You hear the frequency of the ambulance siren change pitch as it's traveling to you, and then as it's moved right at you, and then as it's moving away. So while it's moving towards you, while it's on this side, you hear a higher frequency, and then as it moves to the other side, you perceive a lower frequency. Okay, so there's that real sound as cars drive by and things like that. Okay. So the closer the speed is to the speed of the wave, the more the frequency shift is observed. So the faster that ambulance moved as it was moving towards you, the higher that pitch you would notice as it was moving towards you, and the faster it was moving away, the more you would notice that lower shift. This also happens if a sound wave or any wave is reflected off of a moving object. So if the object isn't moving, the perceiver over here is perceiving the exact same frequency as the source of the balls in this case. Okay, if the object if these were to bounce off while it was moving towards him, okay, this object would perceive a much higher frequency. It would perceive boom, 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 boom. Okay. So if that wall or reflector was moving towards you, you would perceive a higher frequency, just as if the source of the sound or the wave was moving towards you as well. And if the reflector was moving away, you would perceive a lower frequency, just as if the source was moving away. So boom, 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 etc. Okay. All right. So when does the reflection cause a higher frequency? Okay. It causes a higher frequency when the reflecting object is moving towards the observer. Okay, and therefore when it's moving away, it's a lower frequency. So this shows what would happen if a wave was reflected. Now, which way? So this is my incident wave, and this is reflecting off of this object. And this is my reflected wave. Which way is the reflecting object moving? To the left or to the right? Okay. Well, so the wave is getting longer. What does that mean about its frequency? It means the frequency is decreasing. Okay. So if the frequency is decreasing, which way is this moving? To the right or away? Okay. So all waves exhibit this effect, which is called the Doppler effect, which I can't believe I haven't mentioned before. This is known as the Doppler effect, which you've heard of before. This change is called Doppler shifting of frequency. When you talk about sound, the reflected or the perceived sound wave has a different pitch. When you're talking about light, the perceived light has a change in color, which is pretty interesting. Radar guns actually work on this way. They use an electromagnetic wave that you can't see. Light is an electromagnetic wave that we can see. This is just a different frequency that our eyes aren't tuned to perceive. And they send a known frequency of wave, and then they measure the reflection and the frequency of the reflected wave, and they're able to calculate the speed of the object traveling based on that Doppler shift in frequency. Radar works the same way. Doppler radar, they're able to use the shift in frequency to determine the speed and direction of rain and that sort of thing. Okay. Another interesting wave behavior is shock waves and sonic booms, and we're going to talk a little bit about those now. So here we've got a jet, and these represent the sound waves. Now, sound waves aren't lines, they're compression waves, but we're going to use these to represent the compressions. Well, the lines will be the compressions. So and so the jet is traveling less than the speed of sound, and we're getting some Doppler shifting. We're getting the frequency increase over here and the decrease in frequency over here. So here's a jet that's just breaking the sound barrier, and you can see there's this. It looks like you took a sphere and sort of cleaved off a plane with a plane, a little slice of that sphere. You see another little one right here. So what's going on is as the plane gets faster enough to travel at the speed of sound, the pressure waves build up. So here's the plane traveling at less than the speed of sound. The sound waves are traveling faster than the jet. Okay, here's the jet traveling at the speed of sound, and he's keeping up with every sound wave that he's emitted. And you see all these compressions are building up on the plane. there was a lot of hesitancy to try to break the speed of sound because they knew that this would happen, and they thought that the pressure might destroy the plane. But this pressure buildup over here is what we were seeing on the previous slide with that condensation, that cloud that had formed. This is all those waves building up. Now, if the plane travels faster than the speed of sound, then we get what's called the shock wave. So here he's making a sound, and he's actually, or she is actually outrunning it. And see how these waves intersect along these lines. So these lines are forming where the waves are intersecting, and they can only intersect if the plane is traveling faster than the speed of sound. And that's called the shock wave, this overlap of compressions, and that is what creates the sonic boom. Okay, so this is the shock wave happening. So here you can see this is where the intersections are occurring along this cone, and if you were an observer and a jet was sending a shock wave overhead, then you would perceive that as a sonic boom, which is like a loud cracking sound, because you would hear multiple sounds at one time, which is pretty interesting. So this is a boat that's creating a shock wave, not a sonic boom. A sonic boom is a shock wave in air with sound. This is a shock wave. And in order to create a shock wave, all you have to do is travel faster than the wave velocity itself. So this boat is creating a shock wave because it's traveling faster than water waves. Okay. So here again we're looking at the shock wave that's being created by this jet. Here we've got a person that has not heard the shock wave yet. This person is hearing the shock wave. And then this person just hears the jet noise. Okay, so you hear it kind of all at once. This is if something travels faster than sound, it's called supersonic, by the way. Here is a supersonic bullet right here, and you can see it's leaving two shock waves from the front, the leading edge and trailing edge of it. This is the muzzle blast here. From the expulsion of the powder. So here's again a bullet that's creating shock waves. Now what happens to you as you travel faster and faster? Mach 1 is the speed of sound, by the way. Mach 3.5 means you're traveling 3.5 faster than the speed of sound. So we can see these shock waves, multiple shock waves from multiple interruptions of the air pattern due to the shape of the jet. We see that if the pilot travels even faster, Mach 6, these shock wave lines become tighter, more at a acute angle. Anyway, here's a duck leaving a shock wave traveling faster than the speed of water waves. He's really, or she is really moving, hauling butt here. But again, you only have to travel faster than the wave itself. But remember, a subsonic, meaning slower than the speed of sound, jet or object will never create or cannot ever create a shock wave because the waves will never overlap. Okay, so that is it for today. Enjoy the rest of your day, and I will talk to you later.